Alrighty people, today continuing on with the atom, we're going to be talking about how filaments are different to this sort of thing, glowing elements. The binding energy of atoms, not nuclear, binding energy of the atom, the absorption spectrum, in particular Fraunhofer lines, and fluorescence in terms of the light above you when you're probably watching this video. Alright, let's kick it off. Filaments. A filament is something that looks kind of like that. Alright, what we do is we add heat via some sort of electric current. So this thing's got some internal resistance, there we go. Internal resistance, it's actually not a bad one. Internal resistance, we pass a current through it, it gets hot. It gets hot enough to glow if it's got a fair bit of energy, so a fair bit of current going through, lots and lots and lots of heat building up. What will actually happen is the electrons inside of that filament itself will actually vibrate backwards and forwards. If we give them more energy, they'll be able to do it faster, and the faster they do it, the higher the frequency. So if we put a little bit of energy in, what we'll do is make some of them glow maybe some red. We wind up the voltage a little bit, so we're forcing a bit more current through, and we might get some of them to glow orange. So what we're doing is getting some red, some kind of orange. If we keep increasing, we end up getting kind of yellowish. The average of all these colours is kind of an orangey glow. So imagine you're got an oxy torch on a piece of steel over in tech, and what you're doing is using the oxy torch to heat that steel up. At first it kind of glows a really dull red, and then after a while it'll actually start to glow kind of a yellowy orange colour as you're adding more heat. What you're really doing is making the particles inside that steel vibrate backwards and forwards faster and faster and faster until you've got all of the colours of the rainbow. If we've got something that's glowing all of these colours, it's actually white hot. It's glowing all of the colours kind of equally. If you look at an intensity versus frequency graph, what we're doing is kind of making the peak shift. So this might be a peak that's kind of centered over about yellowish, and what we're trying to do is make that peak kind of shift and spread out so we've got a fair bit of colours all over the spectrum. So we're actually getting, Roy G. Biv, something will glow white. So a piece of tungsten, for instance, in a light globe, like the old style filament globe that used to look like this, or still do, will actually heat that metal up so much that it will glow white, because it's actually got some electrons in there vibrating really fast. They're actually giving off bluey light. Some are actually giving off reddy orange, and all mixed up together it's white. If you look at it through a spectroscope, you'll actually see perfect rainbow. If you look at the fluoros above us with the spectroscope, with the black thing with the diffraction gradient, you actually see a fair bit of red, fair bit of kind of a greenish colour, and a fair bit of blue at the end, and little bits of the other ones. That's actually because you're looking at an emission spectrum, similar but not the same as this thing over here. The binding energy of an atom moving along is equal to the amount of energy it takes to ionize that atom. So in this case over here, where we've got hydrogen, hopefully you remember this from last video, the ground state is 13.6 electron volts down, so we need to give that electron 13.6 electron volts worth of energy in order to make it come up to the top. Now we can do that using heat, or we can make it do that using electricity, and we'll actually ionize, so it will reach a point where that electron doesn't really want to come back anymore, and that electron's escaped. Now we've got hydrogen without its electron, means it's ionized. So the binding energy of an atom is the minimum amount of energy required to release one of its electrons. The binding energy of a nucleus later is to do with equals mc squared. Now, Fraunhofer lines, or the absorption spectrum. If I got hydrogen, a piece of hydrogen gas, just like this one over here, and what I did was heated it up, it would glow a few different colours. We saw from the last video, everything that ends in the Lyman series would be ultraviolet, pretty much everything in the Balmer series would be visible, we'd be able to see the colours that it's glowing, and everything else would be kind of infrared, the heat that it radiates off. Now if I was to get some hydrogen gas, or a sample of gas and I didn't know what it was, and I wanted to find out what it was, what I'd actually do is pass pure white light from one of these light globes through that, and what would happen is the electron inside this hydrogen would actually absorb the frequencies of light, the energies of light related to these gaps. so these gaps here, all of these transition energies, and it would absorb them. And then when the electron falls back down, it would rescatter them off in different directions. So our original white light might pass that way, but then the scattered photons are going all over the place. So what we see is white with colours deleted. Alright, so we're passing pure white light via something that's super hot. I'll get to the Freund lines just in a sec. Passing pure white light through this gas. The gas is absorbing the colours that relate to its transition energies, and then it's re-emitting those things, but it can't re-emit them in in the same direction. So it gives them off in scattered directions. We don't see those lines anymore. They still exist. We just can't detect them. We don't see them unless they're pointed straight back at us, and the majority of them just aren't. If you imagine the sun, for instance, so the sun is this obviously very, very hot glowing thing that's up in the sky at the moment, unless you're watching this at night time, and then it's up in the sky by the other side of the planet. Pure white light coming out of here. So this is glowing so hot, it's giving off Roy G. Biv perfect white light. Look at the sun carefully through the spectroscope and you'll actually see all of the colours pretty much. And then the sun's actually made up of a whole bunch of different elements, and those elements are actually in sort of vapor form on the outside of the sun. So, all the way around the outside of the sun is this huge big gas cloud made up of all the elements that the sun is also made up of. So the white light from the sun passes through this gas cloud, scatters all of these colours that it can absorb, like over here, in all these different directions, and we don't see those colours. So the colours that our sun is made up of, or the gases, elements that our sun is made up of, we can actually find out really, really, really accurately which ones, and also how much, based on the amount of colours that are deleted. So the amount, and how much of those colours are deleted, so kind of related to percentage-wise of whatever's in there. So hydrogen, a lot of that's deleted because that's a lot of hydrogen, but also all of the elements, all of the trace elements that are actually in here. So all of them have got set fingerprints or DNA type things like this. They've all got very, very, very unique emission spectra, which means they've also got very, very, very unique absorption spectra. So if you look at the emission spectra, you'll see bright lines of colour. If you look at the absorption spectrum, you see all of the colour but black bands where those colours have been deleted. The last thing I want to talk about is fluorescence. Once again, over here we have hydrogen, and in the last lesson I was talking about bringing these electrons up to the third excited state, so n equals 4 level, to the point where they're less than an electron volt from being ionised, and that electron dropping down through these energy levels, and it transitioning maybe all the way back down and giving off all of that transitional energy as a photon. It may be that it does a few different type of jumps. What we're talking about here is putting a certain amount of energy in and getting that energy out, but we're getting it out in smaller chunks. So we might put, what have we got here? 10.2 electron volts worth of energy in. We're only going to get that out because there's no other transitions in the middle. But let's say we put in enough to get to just about infinity. What would actually end up happening is we get, some of this photon and some of this photon and some of this photon and some of this one and some of that one and some of this one and that one and all of the other combinations. These are the small chunks we get out are because of the combination gaps, I guess, in the energy levels. So we call this fluorescence, and it's the re-emission of high energy photons, I guess. In fluoro tubes, it's actually ultraviolet light that gets created. The ultraviolet light, ends up somewhere up here in the mix of stuff that's in the fluoro tube, and then it transitions back down in smaller steps. So high energy light as a series of lower energy photons. So we still got the same amount of energy out, we just got smaller chunks. And very usefully, if that's a word, those smaller chunks are actually visible to us, so we can light stuff up.